Bienvenidos, Ushamdi, and welcome, CTS230, Section 841 students, for the first 8-week term of the Fall 2017 semester at Anne Arundel Community College. This is the Networking 3, or the Scaling Networks V6 course from Cisco Networking Academy, and this afternoon's video tutorial is actually going to be an EIGRP supplement, where we're going to be taking another look at summarization, and we're also going to see from some debug output the real benefit, the true EIGRP benefit that comes with summarization. We're also going to talk about distances, and I'm going to teach you a command that you've already seen, but we're going to actually be adding an option to that command, that show IP EIGRP topology command, that's going to help us when we're trying to determine what the slowest link is along the current path and what the cumulative delay is, so that we could then take those values if we wanted to, and we could do a little math and figure out what the composite metric, what the distance is going to look like. And then I've got a third topic, and I'm going to stop at the end of that second topic, and I'm going to warn you that before we get into the third topic, you're going to have an option as to whether or not you want to continue, right? And I'll talk about that when we get there. So let's go ahead and dive in here and start our conversation out with summarization. Now, we know from CCNA studies, and I'm going to move over to router 7 here, and actually before I move on, let's real quickly, we're only dealing with 3 routers here. So router 3, router 7, and router 12. So here are the 3 routers that we're worried about, right? And we've got loopbacks here on all 3 routers, right? We've got this loopback 0 address on all 3 routers. So on router 12, it's just simply 12.12.12.12. On router 3, 3333, and 77777. But we also have some additional loopbacks here on router 7, and that's where the conversation is going to start. And it's on router 7 that we're going to be summarizing these 4 loopbacks toward router 3, who obviously will then advertise that summary over here to router 12. Now, one of the things that we've been told, and the text talked about this multiple times, is when you summarize, right, the benefit is that the routing table, show IP interface brief, is that the routing table shrinks. And so here we can see we've got these 4 loopback addresses, 192.168.4.5.6, and .7. And these are going to very conveniently summarize down to a /22, and it's going to be 192.168.4.0/22. And that's going to include all 4 of these networks here, right? Because these are all /24s, right? So .4.0/24, .5.0/24. And so if I come over here to router 3, and this is what the text is talking about. When I say show IP route, you can see that we've got a lot of entries here in the routing table, and it looks like on router 7, we may have an interface, loopback 5, no shut. So let's bring that interface up. If it was down, okay, it looked like it might have been down there. So show IP route, and you can see we've got all of these networks down here, right? And we only have 4, but what if it was 40? Or what if it was 400 routes? Then you would want, obviously, if you could, you would want to summarize these routes that I'm clearly learning here, right, via the successor, who is the next hop router, and the owner in this case is 10.0.30.7.7. So it's router 7, and you can see it's out that same fast Ethernet 0.0 interface. And so what we would want to do is, in order to save, from a visual perspective, to save us from having to, maybe hit the enter key a whole bunch of times to get through, or the space bar to get through all of the information there, is that we would summarize, and we would try to summarize it down as best we could to limit the amount of entries in the routing table. Now, that is a very common explanation as to why you would do summarization, and at the CCNA level, it makes a lot of sense. But also at the CCNA level, there's something else that we talk about, and it's query messages. Now, if I was to say debug EIGRP packets query, and is there a detail I can put on here? Yeah, I could put some detail on here, but we'll stick with this right here. So debug EIGRP packets query, and I'm going to come to router 12. Remember, router 12 is on the other side of router 3, and it's actually labeled up there router 10, but it's definitely 12. And we're going to say debug EIGRP packets and query, right? And the chapter talks about query messages and the fact that when router 7, and if I pull the diagram back up here, when router 7 loses any one of these loopbacks that he's got configured here, and we'll just put them over here. So here's these 4 loopbacks we've got configured. If that loopback goes down, router 7 is going to enqueue and generate a query and send it to router 3. Now, a lot of times people think that this doesn't make sense, right? That why would 7, who's the owner of the network, why would he ask 3 if 3 knows how to get there? Because 7 owns it and he just lost it. But the problem is that this is, vintage behavior with EIGRP, is that 7 lost it, right? And remember, distance vector, I probably should have said, better way to express it, this is vintage distance vector behavior, because 7 only knows about the network here on router 7. He's connected to 3, but he doesn't know. Maybe 12 is telling 3, I've got this other connection and we can go this way to get to that network, right? Or I'll put a router here in the middle. Maybe we can come this way, right? And it's not connected there. So that's a possibility. And so 7 is going to ask 3, hey, do you know how to get to the loopback I just lost? And 3 is going to send a query over to 12. Now, in this tiny little network here with these fast Ethernet interfaces, this is going to happen almost instantaneously. But think of this on a larger scale. What if there's then an EIGRP neighbor out here, and this is Washington, D.C., and this is Alaska? And then we've got another router in the EIGRP autonomous system over here in Siberia, right? Now, very, very plausible that you could see something like this. So now we're talking about sending query messages across the country and the continent, and then across the Pacific Ocean into another continent, and we would have to wait for the query replies to come back from everybody out here saying, no, I don't know how to get to the loopback network that you just, again, a loopback is I'm simulating it with a loopback, but really I'll draw it like that, right? So it's a network segment, and 7 loses it, and he's going to ask 3, how do I get there? 3 is going to ask 12, hey, do you know how to get there? 12 is going to ask this router here, router X, right? And then router Y. Do you guys know how to get there? And they're going to have to wait for queries to come back saying, nope, we don't have another way to get there, right? And this is typical EIGRP behavior. So let's see what that looks like with no summarization. And remember, we're talking about the key benefit of summarization here. So we'll stick with this one. I'll say shut. So I'm going to shut down the 192.168.5.7. And we should see that router 3 and 12, and did you see that the little blue yield sign popped up? And so here we go. So take a look on router 3, received query on fast Ethernet 00. And that query is asking router 3. It's router 7, and that's the only router on fast Ethernet 00 that can speak with router 3. Router 7 asking router 3. Here's the query. Hey, do you know how to get to the 192.168.5.0/24 network? Because I just lost it. So I'm querying you, my neighbor, because I'm distance vector. I can't see the state of all of the links that all of the nodes have, right? So I'm going to start asking people, do you know how to get there? I'm going to ask my neighbors, do you have another way to get there? And then take a look at what router 3 does. It enqueues a query on FA01. Ironically, this is the interface that goes to router 12, and then the query is sent. Because now 3 has been asked, do you have another way to get there? 3 says, okay, well, 7's asking me, let me check with 12 because 12's part of this EIGRP autonomous system. Maybe he knows how to get there. And if he does, then we can reconverge and I can tell 7, yeah, let's go this way. But we come over here to router 12, and this is what we see. We see that the query is received from router 12, right? And 12 responds back. We don't see that part, but 12 is saying, yeah, no, I don't have another way to get to the 192.168.5. I'm sorry. But you can see that the query comes all the way here to router 12. And in that scenario that we drew up earlier, if there were routers hanging off of router 12 in Alaska, and then another one daisy-chained out maybe into Siberia, and then another one into Italy, we would be waiting for the query, for the reply to come back saying no. And that may take a while, right? And that's where that stuck in active, when we talk about a successor route, right? A prefix, this 192.168.5 in this case, being stuck in the active state. And this is a bad thing because as long as it's in the active state, the routers will not be forwarding the traffic for that prefix because it would be active. In other words, it would have the letter A next to it when I come over here to, we'll do it off of router 3. So on router 3, if I said show IP EIGRP topo, right, I would have for the 192.168.5, it's not here because obviously it's missing, but instead of the P, we would see it here and it would have an A, right? Because passive, remember, P is good. Passive is good. We want the successor routes to be in the passive state because that means that they're converged. When there's an A here, it means that they're active. They're not converged, right? And so that's a bad thing. So now let's bring the conversation, again, in this whole time, everything I've been describing, right, is now going to come full circle with the summarization conversation. This is where the two are going to sort of intersect. So we know how to do summarization, right? And we know how to do summarization with EIGRP. So we know that we've got .4, .5, 6, and 7, and we know that 4 is 0, 0, 0, 0, and this is in binary. And then 0, 1, 0, 0. I know 5 is 1, 0, 1, 6 is 1, 1, 0, and 7 is 1, 1, 1. And I'll put the leading 0 here. So then we find our bit boundary, right? Where do the bits no longer match? And it's right there. And that little trick, right? How many bits are left that don't match? So I take 2 and raise it to x. And x is the number of bits that didn't match. And not the total number, but just the number to the right of this line. So 2 to the 2 equals 4. So this summary that I'm going to do will represent ultimately 4 networks. And again, very cleanly here, we're going to represent these 4 networks. And so I know that this is going to be a /22, right? And what's the value that's here? The last value is 4, and that would be in this octet. So my summary will be 192.168.4.0/22. And we kind of already covered that. And that's going to represent these 4 networks. So we learned early on in CCNA how to summarize. We learned in this chapter how to apply that summary in EIGRP. So I'm going to come to router 7. And the beauty of EIGRP is I could do this summary anywhere. So tonight, when we talk about OSPF and link state routing protocols, you cannot summarize anywhere. It has to be at an ABR or an ASBR, okay? And that's a link state characteristic. With distance vector, this is one of the advantages with distance vector. I could summarize these addresses on any router that's getting these 4 individual loopback addresses. So I could perform the summary on router 7, who's the owner, the originator. I could perform the summary on router 3, who's receiving these 4 individual networks. I could do the summary on router 12 if I wanted to. It all depends on your use case, right? But for our purposes here, and to show the true value of summarization in EIGRP, and to explain to you that it is not simply making the RIB, the routing information database, making that routing table look prettier, right? Or look smaller or more compact. That is not the major benefit of summarization. The major benefit of summarization is that it limits the size of the query domain. Remember the queries we just talked about, right? We saw that router 7, he sends a query to 3 saying, hey, I don't know how to get there anymore. Do you have a way to get there? And then 3 sends it off to 12. And then again, play the scenario out. 12 sends it across the continent to Alaska, and then from Alaska to Siberia, or whatever long distance links you might be using, right? And that takes time because the route will sit in an active state until the queries which require a response, until those responses are received. And we don't want to wait long for that. And so that is the true benefit of summarization in EIGRP, is that it limits the scope of the query domain. In fact, it limits it to the hop after, and we're going to see this, the hop after that summary is received. And so here's what we mean. So let's get into interface. First, we'll bring up the no shut. We'll bring the loopback interface back up. I'm going to come here to router 3, and we're going to say show IP route. And do we see the 4 routes? We do. There they are. Now let's go to router 7. And on router 7, I'm simply going to go into interface fast Ethernet 00, and let me do show IP interface brief. Let's make sure it's 00. It is. So I'm going to say IP summary address, EIGRP, the AS is just 1, right? And now I get to put my summary in here. And the beauty is I can get away with doing my CIDR notation, that classless inter-domain routing notation, commonly referred to as slash notation, right? So here we go, 192.168.4.0/22. Now we're going to see a resync, and this is important because I believe there was a packet tracer activity we did where it showed the adjacency being torn down. This does not tear the adjacency down. In fact, if I say do show IP EIGRP neighbors, right? The uptime of this adjacency with router 3 is 1 day and 9 hours. So not even close to have been reset within, seconds of me running that command. It is a resync. It is a graceful restart, or I should say, yeah, I guess we'll go with that. Well, it's a graceful resynchronization of the routing information being shared from router 7 over to router 3. And we come over here to router 3, and let's scoot up a little bit. So now we've done the summarization. So here is typically, again, show IP route. Here is typically the explanation given as to the benefit of summarization. And from an aesthetic perspective, from a visual perspective, okay, I can buy that, right? We've got 3 less lines in the routing table. It certainly makes sense that it is a benefit, right? But it's not the primary benefit. And we need to stress this, and this is definitely something that you want to learn early on. And again, all of the things we're talking about have been covered in these 2 chapters that we did on EIGRP. It's now simply kind of pulling it together and demonstrating this is what's going on. So now I have this single entry here. Let's check router 12. What does router 12 see? Because remember, router 12 is getting his updates, show IP route, from router 3. And sure enough, right, we've achieved that visual benefit right here. We have a single line in the routing table representing 4, what was 4 lines is now 1 line, right? So we've saved ourselves from having 3 additional lines. And again, when you're saying, you're saving yourself 300 lines, right? That is a huge benefit. But truly, right, truly the benefit is this. And remember, the debugs are still on. So now let's go to router 7 and we'll pull down another interface. I'll say loopback, what do we have? I'll take loopback 6 down, right? And I'll even do this. Actually, I won't do it on, I was going to ping and you'll see that the ping dies, but it's more important that we see the output of the debug right now. So I'm going to shut that interface down. Now, if you look up here at the top, you'll see 10, there's no blue yield sign. 3, there's no blue yield sign. So what do you think is going to happen? Remember before I did summarization, both router 3 and router 12 received queries. 3 got its query from 7 because 7 doesn't know what's going on. He loses it. He's asking his neighbors, hey, do you have another way to get there? Because I'd love to go through you. But this is the benefit. I shut the interface down. There's our yield sign with 3, but nothing here. So let's come to 3. Yeah, he gets a query, right? He receives the query from Fast Ethernet 00 asking, and this is the question that's being asked. 3 receives the query from router 7, and router 7, and remember, this is what 3's rib looks like. This is the routing table on router 3. 7's query packet comes in, and it says, hey, I just lost the 192.168. I think we said 6.6.0/24 network segment. Do you know how or have another way to get to this specific network? And then router 3 looks into his routing table and says, do I have an entry that I've learned via EIGRP for exactly 192.168.6.0/24 in here? Do you see that entry in here for 192.168.6.0/24? You don't, because it's been summarized, right? It sits in this summary range, but router 3 looks at the request from 7 and says, nope, I don't have that. And so at that point, there's no longer a need to send anything over to 12 because this is not in the routing table on 3, and it never was, right? It never was in the routing table. This is what was in the routing table, right? Before, remember, 3 had that route too. Remember when we had all 4 entries in here, 3 had the .6. And it had the 5. And when I shut the 5 down, 3 fires a query over, right? Because there's a withdraw that comes over from 7 saying, hey, I don't know how to get there. Do you know how to get there? 3 says, no, I don't know how to get there. And he's going to ask 12. But now the request comes in and 3 says, yeah, no, I don't even have this route. So I know that I'm not learning it from 12. So there's no need for me to even ask 12, right? Because I never passed it on to 12 because that is not in my routing table. And so that leads us over to 12. And take a look. Right? Is the debug still on? Right? Did it time out? No. The EIGRP debugging, the packet debugging is on. And that is the true benefit of summarization in EIGRP. And it's a very, very critical concept. And so remember, we're limiting the size and the scope of the query domain. And so here's the Alaska router, and we'll play this out. Here's the Siberia router over here, and we'll go over and we'll take it to Italy. And there's Italy. And these guys are all in the same EIGRP domain. But since router 7 has summarized the information to 3, and 3 knows that he sent the summary over here, he did not send the specific network 192.168.6.0/24, right? Because it's been summarized, it's been abstracted, hidden from everybody else in the EIGRP domain. And so 7 will query. So it's going to be one hop beyond where the summary was done. And that is the limit. And so I'll put up the wall right here. So that is how you limit the size and scope of the query domain in EIGRP, is with summarization. Because you go one hop beyond where the summary was done, right? The summary was done here on 7. We go one hop beyond that because 7 is going to ask, right? Naturally is going to ask 3, hey, I just lost this network I've got. Do you have another way to get there? And 3 says, no, you never told me about that. I've never passed that information over here. All I know about is this /22. And since it's not exactly that network you're asking me about, I'm going to reply back to you and say, nope, don't know how to get there, and no need for me to bother everybody over here about that network because I never passed it on to this guy, so I'm not going to query that guy. And again, that is the benefit. It limits the size and scope of the query domain in EIGRP. And if you've ever had to troubleshoot a stuck and active scenario, it is not fun. And so that's summarization. That's why you use it in EIGRP. And this, right, not the fact that the routing table is shrunk and easier to look at from a number of entries perspective, but because it limits the size and scope of the query domain. And again, remember, it's going to be, think of it as +1. So +1 hop from where the summarization is done, that is how far the query domain extends. And so the query domain here is these 2 guys. That's it. Not these 4 guys over here as well. It's just these 2 guys right here. That's all that needs to happen. And so that's our query domain. So now let's move to the distance conversation. And we'll stick with, let me see, I'm going to kill the summarization here on 7. We'll bring the interface back up, no shut, and then we'll go into interface fast Ethernet 00, no IP, summary address, EIGRP 1, 192.168.4.0/22. And so now on router 3, we should see show IP route EIGRP. We see our 4 member routes. Now, working with the metrics. So here on router 3, if I were to say show IP EIGRP topo, right, or I should say the metrics, the distances, right? We're going to talk about the distances, the feasible distance, right, the reported distance. And so here we see we've got the feasible distance is listed here. And the text points out that that is the feasible distance as well. And that this is our reported distance, right? And obviously router 3 has to take into account the outgoing interfaces along the path in order to get the composite metric values, the K1 and the K3 values that it's going to use for, and actually the K1 value is 1. These are multipliers, and these are the only ones that are on by default. Remember, K2 load is off. It's a 0. K4 and 5 reliability, those are 0. And so to be technically correct, the values that we need to get are the delay, the cumulative delay, and then the slowest bandwidth speed of an egress interface from the destination, or sorry, from the source to the destination. And that's what we use here, right? So we get all of the delays and add them up, and we get all of the bandwidths. And then remember, we've got that 10 to the 7 divided by the bandwidth in kilobits per second. And we put that, I'll put that here. And then we're going to add that to the delay divided by 10, because we need to get it into tens of microseconds. And what we look at is microseconds when we get the interface output. And then this whole thing gets multiplied by, and I'll put it down here because I'm out of space, by 256, right? So rather than do this, so if I was in, actually let's switch over here to router 7 because this will make it a little more demonstrative. So on router 7, do show IP EIGRP topo. And we should see a 12, 12, 12, 12, and there it is up here at the top, right? And it's in the passive state, and here is the feasible distance. here is what you are told the feasible distance is, and they happen to be the same right now, and here is the reported distance. In other words, this is what the successor is telling me their cost to reach this destination. The successor is router 3. That's that via line. And so router 7 knows that the successor through which he will go to get to this successor route, the 12/12/12/12/32, is going to be router 3, and that is his feasible distance, right? And the route is in the passive state right now. We know that the outgoing interface is fast Ethernet 00. So this simple option to the show IP EIGRP topology command will save you from having to do the following. Okay, do show interface fast Ethernet 00. All right, so the bandwidth of this, and this is what you would have to do if you're manually walking through this. All right, so it is 100 megabits a second, so it's 100,000 in kilobits per second. I'll write that over here, and my delay is 100 microseconds. And that's the first outgoing interface, right? Because again, remember, we're on router 7 right now, so we just looked at that egress interface. So now let's look at this egress interface on router 3. So now we've got to come over to router 3. And I come over here to router 3 and I say, show IP interface brief, actually. I'll make sure I get the right interface here because I need the interface fast Ethernet 01. So show int fast Ethernet 01. And I see, okay, it's 100,000 again, right? So I don't need to put anything here because it's the same, right? So these could be the lowest. And then the delay is 100 microseconds. All right, so now let me go take a look at router 12. So now I come over here to router 12 and I say show interface loopback 0. And we see what? We see that the cost to reach loopback 0 is 8 million, 123, 123. So it's 8 million, right? In terms of the speed in kilobits per second, 123, 123, and the delay is 5,000 microseconds, right? So I've got everything I need here. I've got my delay, and I've got my bandwidth speeds, and there's no question, right, that which is slower. Is 100,000 kilobits per second slower than 8 million? This is kind of a gimme, right? So we've got 100,000 here. And we've got 5,200 here. So now this 100,000, remember I've got 10 to the 7, so I would take away 1, 2, 3, 4, 5 zeros from my 10 to the 7, leaving me with 2 zeros after it, and then divide this by 10, so I get 100 plus 520, and we're going to run this through the Python script. So I get 620 times 256. And that should give me the cost that we see over here on router 7. And so we should see, and actually if I scroll back up just a skosh, we should see this, 158,720. So let's quickly pull up, and where's it at? Here we go. So here's our Python script. Let's rerun it. And we say the slowest bandwidth is 100,000, 123, and the cumulative delay was 5,200, and there it is, 158,720. We come back to router 7, and we say, okay, that worked great. Now, that's manually having to walk through every egress interface. Again, remember the scenario where you've got 6, 7, 8, 9, 10 routers in between the source and the destination, right? A much easier way to do this, and we'll do it on router 7, is show IP EIGRP topo and then put in the network that you're looking for. And take a look at what we get. That option, by putting the network in along with the CIDR notation, of which you're interested in seeing, okay, what is the minimum bandwidth along the path? And what is the total delay in microseconds along the path? And it gives you the information right there, right? So again, very, very important option to the EIGRP command. All right, so it is right here where I'm going to advise you that if you are not interested in going down the rabbit hole on the distances, because I'm about to do this right here. I'll pull out the scene from The Matrix, and I'm basically presenting you with two options. Take the blue pill, and you can go back to your CCNA studies, and the rest of this conversation never happened. Or you can take the red pill if you want to find out the truth and you want to go and see just how far down the distance rabbit hole we can go. And so again, very important that we cover this. So I warned you, if you're not interested in what I'm about to talk about, which is going to be the computed distance and how the feasible distance is not, as it's depicted in the text, is not the feasible distance. And I'm going to demonstrate for you why that is the case. So let's do this from, so we've got that 12.12.12.12. And so from router, so we'll do it from router 7's perspective here. So here we go. So show IP EIGRP topo, right? And the text tells you that the first number in the parentheses, and there's multiple images like this, that the first image in the parentheses is the feasible distance. Again, I am here to red pill you. That is not the feasible distance. That is what is referred to as the computed distance. And I know what you're thinking right now. Travis, you probably just made that term up, computed distance, right? I'm telling you, I am not making that term up. And what becomes so confusing for learners is they see that it says feasible distance here, right? And then they look and they see that, oh, well, that's the exact same value as the feasible distance. So that is the feasible distance. It is not the feasible distance. In fact, when you see from the output of the show IP route command, show IP route EIGRP, and let me bring it up a little higher here. When you see the metric displayed here, you are also told that this is the feasible distance. That is not the feasible distance. That is the computed distance. And to make sure that I put some weight behind what I'm telling you, let's pull up the RFC for EIGRP, RFC 7868. And I am going to dig through here and I'm going to look for computed distance. And you'll notice there's only two matches. You can see right up here, there's only two matches. And let's read this. It's the total distance, the metric, along a path from the current router to a destination network through a particular neighbor computed using that neighbor's reported distance and the cost of the link between the two routers. Exactly one computed distance is computed and maintained. Now, let's go to see where the next occurrence of that is. And it's here. The reported distance is the computed distance as advertised by the feasible successor. So in our case, if we're on router 7 and we see that the computed distance, right, or we see the reported distance from router 3, and let's take a look at that. So here's the reported distance from router 3's perspective. Router 3 tells me, hey, that is because here, this is my successor, right? So here's my reported distance. This is my cost. But what that is, right? It's the reported distance coming from router 3, but on router 3, it's router 3's computed distance. The feasible distance is never communicated between EIGRP speakers. It is a locally significant value, and we're going to talk in a couple seconds about why it's local and what it does locally, okay? And so this is router 3's computed distance, right? But from router 7's perspective, we call it the reported distance. But that is router 7's computed distance. And this is router 7's computed distance. And now I'm getting ready to give you the red pill, because now I'm going to show you, if I were to go into and let's see, show IP, I think it's fast Ethernet 01, and it is. So if I was to go into global config and down into interface fast Ethernet 01, and remember, this is the outgoing interface, so we're going to manipulate the delay on this interface right here on router 3, right? Because that is the outgoing interface through which router 7 has to go to get to that loopback address. So I'm going to tweak the delay here. We're going to change the delay, the K3 composite metric value. And let's see what's going to happen. Because if what I'm telling you is true, then the computed distance should change. But if what I'm saying is not true, then the feasible distance and that number, that first number in the parentheses and the second number after the slash and the show IP route, those will stay the same, right? So I'm going to say, and if we were to take a look at the delay right now, if I were to say do show interface fast Ethernet 01, the delay is 100. But remember, that is in microseconds. When I manipulate the delay, and we talked about this in class, this is critical, the value that I'm entering is in tens of microseconds. So whatever I enter in here is going to be multiplied by 10. So I'll put 11. So the delay is 11. So now let's come back to router 7. And now let's continue this conversation of show IP EIGRP topology. And I don't need to see it. I won't do it for the specific route. And now this is very, very interesting, isn't it? So here's the 12, 12, 12. That again, and if there were more prefixes over there that we were learning through 3, we would see this exact same behavior. But I'm focusing it just on this one to keep it simple. So here's my feasible distance, right? It's still 158,720. But looky what just happened here. Why is that not the same as that? Why is this number, which you're told is the feasible distance, why is that not the same as the feasible distance? And lo and behold, we now see that this is the computed distance. And so watch what happens again. And so let's do a couple more values. So I'll say delay 12. So I'm manipulating the delay ever so slightly to ensure that this prefix doesn't go active, right? That it doesn't go active. And it's important. So now it's 159,232. But the feasible distance is still the feasible distance. Well, let's go back over to router 3. Let's change the delay to 13. And now let's come back over here to router 7. Whoops. There we go. And now we take a look. Now it's 159,488. But the feasible distance is still the same. So while this number continues to change, and we'll come over here and say delay 14, and we come back over to router 7. While that metric continues to change and continues to increment, right, because we're bringing the delay up, we're adding to the delay, right, 159,744, this is still 158,720. And here's where we end our conversation. And actually, do show IP route EIGRP. What number do you think is going to be in the output after the administrative distance and the slash? Is it going to be 90/158,720? Or is it going to be, I shouldn't say // or is it going to be 90/159,744? And I should probably say show IP route EIGRP here. Show IP route EIGRP. All right, and so take a look here. Well, that's interesting because, again, you've been told that that's the feasible distance. It is not. It is what the RFC has defined as the computed distance. It's the computed distance. It is not the feasible distance. And I've just proven to you that it is not the feasible distance because I'm manipulating the number, forcing that number to change, right? Forcing the number to change. And if we look at feasible distance, there's an important, and there's only 3 matches for feasible distance here. And this is where it becomes very, very important. Defined as the least known total metric to a destination from the current router, and here it is, this is all you need to read right here, since the last transition from active to passive. It is a record of the smallest known metric since the last time the network entered the passive state. The feasible distance, and I'm sorry, my highlighting here is way off. The feasible distance is not necessarily a metric of the current best path. We just saw that. Exactly 1 feasible distance is computed per destination network. Nowhere in here does it say that the feasible distance is then communicated to other EIGRP speaking neighbors, because it is not. The computed distance is. And so the feasible distance is nothing more than a historical record of what the best metric was at the given point from when that route last went from active to passive. So the last time it was active and then came, and it could be maybe the router rebooted and then it would have gone active and then it would have come back and been passive, right? Or maybe the interface went down and then the interface came back up. It would go active and then it would come back and it would converge and it would be passive. And at that point, the feasible distance value, which is that value, is logged on the router because the router must keep, and I'll explain here in about 2 seconds why, the router has to keep the all-time best lowest cost that it ever had to reach that prefix. Because while this may be changing, the computed distance may be changing, the feasible distance must remain the same. And here's why. Because let's say that I've got a router here and a router here and a router here, and we'll put one here, right? And these guys all speak with each other. This router right here has to keep track of the best cost, because if for whatever reason it loses this route and the route goes active, it needs a record of what the best cost was to avoid loops, so that it doesn't say, oh, well, you know, that's the cost now, and so then I might be able just to go this way as well if this was a feasible successor, right? If this is a successor and that's a feasible successor and I don't keep this in mind, I may immediately start forwarding traffic this way, not thinking, right, or not knowing that at some point that was the best cost, even though maybe this degraded, and then went down. And that's why EIGRP computes the feasible distance. That's why it holds on to this value. And that is why this is not the feasible distance. And so again, right, you're not going to see this, probably, I wouldn't think you're going to see this on the CCNA. I've actually opened an errata request on the text for Scaling Networks v6 asking that they simply introduce the computed distance definition in that term. They introduce the computed distance term and go ahead and just explain it, right? And say, you know, that, hey, the computed distance can change. The feasible distance is going to stay the same until the route goes from active to passive. And so watch what we mean by that. So let me come back over here to router 3 and I'm going to say delay, and I'll do a question mark, and I'm going to do this. And my guess is that will probably, I would think, that might cause an issue. Let's see. Maybe it does, maybe it doesn't, or maybe I'll lower it down to some crazy low value. And, oops, sorry, I wanted the EIGRP topology. I apologize. Whoops, EIGRP topo. All right, so did that push the route to the active state? It did, because now these numbers are the same. But remember, feasible distance is a point-in-time value. And the reason I gave you the red pill, blue pill is that in your CCNA studies, right, go with feasible distance. If they ask you, hey, what is this value known as? Go with feasible distance. If they ask you what the value in the show IP route command, the second number is, go with feasible distance, right? But I really would like to, I would hope that at some point here in the future that they're going to simply introduce computed distance as the term, right? As the proper term, because again, you don't want to go forward in your studies thinking, hey, this is the feasible distance. And then someone says, no, that's the computed distance. And you're like, no, 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 it's the feasible distance. And this is one of the reasons, right? It's, again, unfortunate. And I'm sure there's a reason as to why they didn't introduce it. Maybe it's like, hey, that's too many terms, or, you know, but again, I'm a big believer in simply explaining, you know, instead of hiding details from the learners, is to give them all the information, right? And to make sure that it's accurate. Because at the end of the day, that's the important thing, is that you're getting the information is accurate. All right, so I'm assuming that if you made it this far, that this is you over here, right? And that is going to wrap up this supplement. So again, we talked a lot about summarization and the true benefits of summarization. We talked about calculating the distance, right? The metric, and an easier way to do that by adding that prefix and prefix length and CIDR notation to the show IP EIGRP topo command. And then we red pilled it. We went down the distance rabbit hole and looked at the feasible distance and the computed distance, right? A new term, trust me, it's there, it's in the RFC, and that is what that number is, right? That is what that number is. And the reason that the router keeps the feasible distance is loop avoidance, to make sure that it knows what at some point in time in the past, what the lowest metric was, so that it doesn't cause any loops. All right, guys, thanks so much for watching, and I will see you in a couple hours.